Hello, this is Module 3, Video C, and we'll be talking about variable transformations in multilinear regression, why we would want to do them, and how we'll do them in Python. So first of all, in the first video in this module, we talked a little bit about how linear regression has certain assumptions and that it does the best when the data meets these assumptions. So the two assumptions that we'll be looking at closely in this section is first the assumption that the data has a balanced distribution, which results in normally distributed errors, and second, the assumption that the predictor variables have a linear correlation to the response variable. So first of all, talking about balanced data. Now, when we say that our data or a distribution is balanced, that means that there are equal amounts of data on either side of the mean. So, for example, right here, let me run this code. Well, you can see that I already had ran the code, but it shows here histograms of each of our predictor variables. So if we go down and take a look at Knox, here's a really good one, MedV. This is a good example of a fairly balanced distribution. If I had to look at this and guess where the mean was, I would guess that the mean is probably right about here. And we have roughly equal amounts of data on either side of it. So as I said, that is a balanced distribution. However, if we come up here to crim and we look where the mean would be, well, most of the data is right here, but you can see that we have a few points all the way out here. And even though there aren't very many data points out all the way out here, because they are very high, they're going to skew our mean upwards. So I wish I'd printed these off actually to show the mean, but the mean of this data, might be somewhere right in here. And you see that there are way more data points on the left side of the mean than the right side of the mean. So that's what I'm talking about when I say that the data is balanced. So here, a few of our distributions are balanced. I'd say RM looks pretty balanced, MedV looks pretty balanced. Even LSAT and Knox, they're comparatively well balanced, but a lot of our distributions here are not balanced at all. And so there's a couple reasons we care about this, but one of the most important is when you have really high out points, like you see here in crim or you see here in ZN. These data points that are far away from the mean can end up having an undue influence on how the line is fit. So if you have a point that is really far from the mean, and then maybe it's also doesn't follow the trend of the rest of the data, these one or two points that are really far away and in a weird place, they'll have very high residuals. They'll be very far from the rest of the line. And so the model will adjust to kind of favor these points, even though it means that it doesn't fit the rest of the data very well. This is a little hard to explain without pictures, so I've linked a video here to a video by Khan Academy, which goes into this a little bit more. But yeah, pretty much when we have uneven distributions, which are skewed, it can cause certain points to kind of throw off the whole model because they're so far away from the mean. So that's something we want to avoid. Another thing that we want to, the second thing that we said we wanted to check for was a linear relation between our predictor variables and our response variable. So right here, what we've done, just using this code, is we've gone ahead and plotted scatter plots of each variable, where medv is the response and based on these input variables. So we can see here that a few of our relationships are linear. If we come and look at RM and medv, I'd say that's a pretty good linear relationship. If we come here, LSAT and MEDV, that's a negative linear relationship, but pretty linear. So we have a few linear relationships, but some of these really aren't. Like, say in this one, you can see a trend, but I'd say it's a little more curved, not super linear. Same here with dis. Maybe we have a trend going about like this, but that's not a perfectly linear trend. So between looking at the histograms and looking here at the scatter plots, what we've surmised is that our data doesn't look how we would like it to look. So what can we do? We can just say, oh well, I won't use linear regression. That's an option. And in some cases that is the best conclusion. Sometimes you look at your data and linear regression just really isn't a good fit for it. However, there are also things we can do to kind of shape our data into the shape we want it to be. So that's where variable transformations come into play. So when I say variable transformation, that literally just means that you are, instead of modeling the variable, you are going to model a function of the variable. So if we come down here, what we're going to look at is doing a natural logarithm transformation. Often in data that occurs in nature, logarithmic relationships just honestly happen to be very common. And so one of the easiest transformations that we can do to often fix our data is to take the natural logarithm of the variable. And oftentimes that will really help with our uneven distributions. So what we're doing right here, first we are creating a data frame. We want to create just a whole new data frame where we have applied a log transformation to all of our variables. And then what we're going to do is we're going to look at the plots of the original data frame and the plots where we have applied a log transformation and kind of see which ones are better and which we want to use. So first what I'm doing right here, creating a new data frame called logdf with all of the variables except for medv. I'm dropping that out. And then what we're doing right here, this is actually applying the transformation. So I'm using the numpy.log function, which does a natural logarithm. And then I'm inputting the data frame. And the +1 is because if we look back up at our data, we don't have any negative values in our data, but we do have zeros in our data. And zeros and natural logarithms don't play nice. Zeros undefined, so we don't want to be feeding our natural logarithm a 0, so we're just going to add 1 to each. So where is this at? Right here. Yep, okay, so we transform that, and then we're just going to plot out those histograms and plot out those scatter plots again. So if we look down here, so these are the scatter plots and histograms of the transformed variables. So, the thing to really do, I should really just plot these out by each other. That would make it easier. Let's see. So let's come and grab our original histograms. And let's just plot those out. We'll just plot them right above. Okay, and run that. So now this first set of histograms, these are our non-transformed variables, and then down here we have our transformed variables. So we're going to look back and forth and see, okay, are there any of these variables where transforming them has made the data more balanced? And if we feel that it has made the data more balanced, then we're going to keep that transformation. I'm going to make this just a little smaller. Sorry, it's probably going to get really small on your screen, but so we can see both at once. So looking at crim, first of all, well, I still wouldn't call this one balanced, but it is more balanced, so I'm going to write down crim. When data is really, really skewed like this, it's hard to entirely fix it, but anything we can do to help it is good. Zien, same thing. It's still not great, but I'd say overall it's more balanced. Looking at Indus, I don't know. Honestly, I'd say that 6s. I'd probably leave it. Chas is just 0 and 1 data, so you can't really try to balance that. Nox, I would say looks a little more balanced in this second one. Let's write that one down. RM is really good in both, so let's just leave it untransformed. Age looks better in the first one for sure, I would say, so we definitely don't want to transform it. This is a big change. We go from completely skewed data to almost normal looking data. That's definitely one we'll want to keep. Let's see, taking a look at rad. Could go either way on this one. I'd probably say the transformed is a little bit better. Tax, honestly 6s, probably just leave it untransformed. P ratio, I guess this second one's a little better. Let's write down that one. B is just bad. And then LSAT I would say is better with the transformation. Okay, so that's been looking at transformations and which one might be better. On the distributions and which one might be better. Now I'd like to look at the linearity. And see if we've had any improvements there. So actually, here, I'm just going to do this. Let's go and I'll screenshot. Screenshot you. And we just kind of pull this up and look at it alongside. There. Okay. So in my screenshot, that's untransformed. This right here is a transformed. So looking at Crim, we thought it looked more balanced in the new one, and I'd also say the relationship looks a little more linear. Zien, honestly bad in both. Indus, I'm not going to try to say anything there. They're honestly both pretty bad. Let's come and grab the next row. Okay, looking at Chas, nothing's going to make that relationship linear. Nox, wait, am I looking at the right? Yeah, I'm looking at the right one here, sorry. Nox, kind of bad either way. RM is good in both. Let's see, okay, now we want to look at age, the one with age. Come up, take screenshot. Drag her on down. Sorry, went to the wrong screen over here. Let me. Ooh, I did not want you that big. Sorry about this. Come on. Okay, shrink down. And shrink this way. Okay, there we go. Looking at age. Both kind of bad. I'd say age is a little better in the transformed one though. Oh, that isn't one that we'd already written down for. Interesting. We didn't think the histogram looked better, but I would say, well, that's hard. Let's see how the histograms looked. On age. Ooh, okay. Histogram was definitely more balanced before the transformation. So, yeah, we'll leave that one untransformed. because, I don't know, it maybe looks more linear after the transformation, but I wouldn't say it's a big difference. So let's just leave that one untransformed. Dis, yeah, honestly, it's kind of bad in both. Rad, hopeless. Anyway, I won't take you through these last through, but you get the idea. We're trying to see if they've improved after the transformations. And I would say that about half of our variables have, from what I've written down here. So when we come down here, we have, we have that crim, zn, indis, age, rad, and dis improved. So we're going to keep those transformations and leave the rest. So what I do right here is create a new data frame. I'm going to call this one model df because it's what I'm going to do my model on. And then in that, I'm going to replace certain columns with these transformed columns. So that's kind of the basics of transformations. In this example, we only looked at logarithmic transformations. There are other transformations you can do. You can do square root transformations. You know, we could spend some more time and really try to look into things and see, okay, are there any other transformations we can find that could fix this data? Maybe we would find some. For the sake of this video, I'm going to pause here, but it kind of gives you an idea of what we're trying to do. We'd love for data starts off linear, but even if it doesn't, we can massage it a little bit, fix a little bit, make it a little bit different. So the next video will actually be building our model.